Hello, one and all, Jake here. Geometry is one of my favorite branches of math. I think it really tests your fundamentals, and here we have a geometry problem that you have definitely never seen before in your life. So let me just lay out the problem. I use some notation here, but let me explain in words what's actually going on. Here we have some figure. We have a quadrilateral ABCD. We have a triangle EFG. We're also given the following information. By the way, I upgraded to an expo marker, like an actual human being, so clap for me. AF equals CE. That means the length of this segment AF is equal to the length of this segment CE. So we're gonna mark them with congruency lines, I guess you would call those. I don't know what they're actually called. Same thing with BG and DE. So these ones get like a double, yeah, to show that they're congruent. And then lastly, we're given that the area of ABCD, so the area of this quadrilateral, is 1. And the problem is we want to find the area of triangle EFG. Before you give this a try, let me just state something that we're going to be approaching this problem with. We are going to say that all we know, we don't have any like crazy information. What we know is that the area of a triangle is 1/2 of the length of the base times the height. And then the other thing we know is that the sine of an angle is, in a right triangle, the length of the opposite side divided by the length of the hypotenuse. That ratio is the sine of that angle. And this is just the definition of sine. So these are the only two things we know. And using just those two things, we can solve this problem. We can prove that the area of EFG is equal to something that we can know. So give it a try. This restriction, it might, seem like it makes the problem harder. You don't know much, but it might actually make the problem easier to sort of guide your thinking. If you're like thinking of a solution where you need to know something else, it probably is a dead end. And so, yeah, go ahead, give it a shot. All right, I'm guessing that by now you've paused the video and tried it if you are at all interested. So let's start to solve the problem ourselves here. Where do we begin? Well, we want to find the area of EFG. That is a triangle. Oh, hey, look, we have a formula on the board for the area of a triangle. That's pretty nuts. Before we do anything with this, I need to elaborate on what exactly we're talking about here. All right, area equals 1/2 length of base times height. Let's elaborate on this a little bit. Let's say we're given a pretty normal looking triangle. It's not a perfect equilateral, but it's an acute triangle. Things kind of make sense when you envision a triangle in your head. You're probably envisioning something like this. B stands for the length of the base. What the hell's a base? As it turns out, it's just the length of one of the sides of the triangle. So let's just say we have triangle XYZ here. And, for the sake of illustration, we'll just say that XZ we're taking as the base, right? So we'll say base XZ. The height, then, what you do is you go from whatever letter is missing on the base, which is Y in this case. In other words, you from the base go to the opposite vertex, and you have to draw a line down to the base forming a right angle. And as you can see, that is sort of like how tall the triangle is. And so height line from opposite vertex to base. I don't know why I did the definition here and like the example here, but it doesn't matter. The point is, take your base, do the opposite vertex. You have to make a altitude. This right angle dotted line I drew here is called an altitude. And there's a very specific reason why it has to be a right angle. And that is, what if you drew this line here? Right? That's still a line from the base to the opposite vertex, but it's not really a height, right? It's longer than the height should be because it's sort of like diagonally tilted. And so what you really want is the shortest possible distance from the opposite vertex to the base. And that shortest possible distance is only given when the line you draw makes a right angle with the base. All right. If you want to take YZ as our base instead, what would we do? We would take the opposite vertex, which is the missing letter, in this case X, draw a line from it, making a right angle with the base. And so this would be the height, the length of this line. And I will leave as an exercise to you. If we chose the base XY, you can draw the line from Z to XY, do it on a piece of paper or whatever. Take a screenshot and do it in MS Paint. I really don't care. As long as you get the concept, that's what matters here. Now, let's just get rid of this. All right, let's just get rid of this right here. What if we have a triangle that doesn't look like the triangle I just drew, right? What if we have a triangle that looks a bit more like this? Right, so we got X, Y, and Z. Then what? Well, it is still a triangle, right? I can't lie to you. It's definitely got three sides. But what if we take YZ as our base? Then what? We draw a line from X to YZ, making a right angle with it. But it seems like no matter what we try, if we try drawing a line from X to this base, it will never actually make a right angle. And you could try it yourself. I mean, make this line, it's not a right angle. Make this line, it's not a right angle. That's even worse. If we keep going that direction, it'll probably get worse and worse. And, you know, we could get real close, but we would sort of have to pass Y in order to do it. And actually, that is what you do. So we need to modify our definition of height here a little bit. Line containing base. That's right, so you extend this outward. And then you can draw your line from the vertex down to this line. And then all of a sudden, a right angle is possible. All right, so let me make an even better illustration to show this next point. All right, so let's go back to this more normal looking triangle. Then we'll repeat what we're about to do on the obtuse triangle, and we'll have to make a minor modification. What do you say let's find the area of this thing given the following information, all right? Let's say we're given the length of YZ, the length of XZ, And can you imagine what else you might know about this triangle? That's right. Let's just say we're given the measure of alpha, where alpha is this angle formed here between yz and xz. Given just these pieces of information, we can actually find in numbers the area of this triangle. So how would that work? Let's see. We're given the length of yz and we're given the length of xz. So what we ought to do is take one of these givens as our base. In this case, let's just choose yz. It's the natural choice, is at the bottom of the board. And we'll draw the height from x to that base, or the line containing it, which happens to be on the base itself in this case. So notice what is sort of happening here. We have this big triangle, but then we have a little right triangle as well with our alpha inside. And since we know the definition of sine of some angle, it's just the in a right triangle, the length of the opposite side divided by the length of the hypotenuse, right? Let's use that definition here. We'll say that the sine of alpha is opposite, which would be the height. That's what we're solving for. Divided by the length of the hypotenuse, which in this case will be xz. That means that the height is just xz sine of alpha. And since we have the measurement, we can find the sine of alpha, obviously. And therefore, the area equals 1/2 of what we're taking as the base, which was yz. And then the height, which is xz sine of alpha. And well done, we've just found our first triangle area. Obviously, you would have to substitute whatever numbers you're given in, but yeah, that is the basic concept at work. So to reiterate, we have this angle right here that is sort of opposite to the height we drew. If you multiply the sine of that angle by the length of the actual triangle side, you end up getting the height. And then we can multiply that by the base, right? So that's the key idea here, is that if you take this diagonal sort of length, the actual side of the triangle, the amount of that length that is vertical to the base is proportional to the sine of alpha. If you recall from earlier when we were trying to make the height of the obtuse triangle, the lines we kept making were like too long. They weren't getting to the line containing the base fast enough, and that's why there was never a right angle. The sort of more diagonal things are to the base, the longer they have to be to eventually reach the base. And that the sine right here, the sine of this angle right here, sort of tells us just how much of an effect this diagonality has. I think I made up that word, but hopefully that made the explanation make more sense. Now, I know that's kind of a loaded concept to grasp, but practice it enough times, eventually you'll understand. All right, so let's try to do something similar with this triangle right here. Let's just say we're given this angle as our alpha, right? And then we're also given the length of xy and the length of yz. let's find this freaking area. So what would we have to do? We would have to choose which of these to take as our base. In this case, I'm going to choose YZ. Again, natural choice. It's sort of like pointing towards the bottom of the board and sort of the base. I don't know. So we have to draw a line from the opposite vertex X to the line containing the base. So let's extend this outward here and then draw a line from X to it, making a right angle. All right, and we're also given the measurement of angle alpha. All right, so sort of the problem here is that our definition of sine doesn't exactly do any heavy lifting. The right triangle we have here, it actually doesn't involve alpha. So we kind of have to construct a new angle right here. And if you go in a half circle, that is pi radians. And so this angle will be pi minus alpha. But if we got the measure of alpha, then we can find pi minus alpha. And now all of a sudden we have a right triangle type setup that we need in order to find the area of the triangle, right? By the way, if you're really bothered by the fact that I used pi instead of 180 degrees, I mean this with the utmost respect. Please grow up. Yeah, start thinking in radians. All right, so our area here will be 1/2 times the length of the base, which is our given YZ, times the height. What exactly is the height here? Well, we know that sine of pi minus alpha is the length of the opposite side, which in this case is the height we want, that is the altitude we drew, divided by the length of the hypotenuse, which in this case is our xy, which means that h equals xy sine of pi minus alpha. So basically the same thing we had before, except instead of using the angle we were given, we kind of had to use the opposite angle. But the same principle sort of still applies. So let's sort of plug that in here. A equals 1/2 YZ base, and then height x, y, sine of pi minus alpha. All right, so now we have an expression for the area of this obtuse triangle. But there's one more thing I want to go over. So let's just say that this angle is our alpha. In order to find the area, we would need to be given the following information: length of YZ, the length of XZ this time, and the measure of alpha. Now, the reason why we have to be given XZ instead of XY is because whatever angle you're given, in order to fully characterize the triangle, you need the lengths of the sides that form that angle, right? So in this case, YZ and XZ form the angle, and so those are the givens. But then we could find the area of the triangle. We drew the height in the exact same way as before. And so we have a huge right triangle here with this angle alpha on the outside. So we have that the sine of alpha is the height we want divided by the length of the hypotenuse. In this case, the hypotenuse is xz, the big side. So that means that h is xz sine alpha. And what that means is that our area is just 1/2 length of the base, which again is yz, times the height, which is xz sine of alpha, right? Now this sort of version of the problem where you have an obtuse angle in the triangle, but that's not the given angle. It's not actually used in the problem. I just wanted to make sure that you knew how to handle it in case it ever does come up. And it will at some point in your math career if you choose to pursue any more math. All right, welcome back from our elaboration session. And so now we know exactly what we're talking about when we say area of a triangle is a half BH. So in order to find the area of VFG, we need to take one of the sides as the base. It might be tempting to use FG because that is like close to what we see as the bottom of the triangle on the figure. However, if you try that, and you can go ahead and do it yourself, I'll leave that as an exercise to you, you'll find that it kind of goes nowhere. Let's choose a different one. Let's choose EF as our base. All right. So then we draw a line from the opposite vertex here to that base. It needs to go at it at a right angle. And so it would look something like this. Let's also mark this angle as alpha. And that it should be clear why from our explanation that we just went over. So what is the area of VFG? Well, that is simply 1/2 of the length of the base, which is the length of EF, times the height. Now, what is the height here? Well, that is just going to be the length of EG here times the sine of that angle alpha. All right, so then we have this nice expression. We can sort of expand it out a little bit though, and we're gonna want to actually do that. So what we'll have here is 1/2 still EF. Let's just, I don't know, just for the sake of it, or we'll write that as FA plus AE, right? We can see that those two line segments add up to EF. And then we'll do the same for EG. Then we got the sine of alpha. Let's not forget that. Okay, cool. All right, so now I have this nice big long expression for the area, but we don't really have anything to do with it. Maybe it's worth looking at this problem from the other side. Let's try to find the area of ABCD, and maybe we'll see something that kind of resembles this, and we'll see if we can maybe make them meet in the middle a little bit. So how would you find the area of this quadrilateral ABCD? What is an expression we can write for it? Here's the problem. We don't have the area of a quadrilateral as a formula on our list of knowns. So we don't know anything about how to find the area of ABCD. Or do we? Because as it turns out, we can sort of split ABCD into two different triangles. So here we have this, I guess, upper triangle. In the red here, and then in the blue we're gonna draw the lower triangle. We're gonna shade it in. All right, cool. All right, so what this really is we'll call this A2, the second area we're calculating, equals just the area of ADC plus the area of ABC. All right, so what are these? If we draw a line from the opposite vertex of this base AC to the base, we can see that this height makes a right triangle along with angle alpha that we already have. And so if we want to find the height of this whole triangle ABC, we'll take our little altitude that we drew here, and we'll take the other side of that triangle, the one that's not aligned with the base. So that would be EB. And then we take the sine of alpha. And then we just, that would be the height, so we multiply by a half base, which would be 1/2 AC. All right, cool. What about the other triangle we have here? Well, let's do something a little bit clever here. And if you've taken geometry before, I know I'm doing this in a very long and elaborate way. But this angle here, it would be pi minus alpha. Right? Because this whole entire thing would be pi. We have the alpha part, and then we have like the non-alpha part. And it forms like a half circle if you combine those two angles. And if we keep going, we get another angle, which is just pi minus alpha. Now let me write this down here real quick in a box, I guess. Pi minus alpha. If you actually distribute the minus sign, that is just pi minus pi plus alpha, and that's just alpha. So actually this angle right here is just alpha. And that turns out to be all we need, because what we can do now is draw another altitude right here. It's a right angle. We have this angle alpha. This figure's a mess right now. Don't worry, I'll fix it. So that would mean that the height of triangle ADC is the length of this line segment DE times the sine of alpha and then we have to include the half base part, and the base is just AC. Okay, so let's clean this expression up a little bit. This is just 1/2 AC DE plus BE sine of alpha. All right, so now we have this expression, but we can actually, we have AC here. That's a pretty big line. It actually can be broken up into two different segments. So let's just do that real quick. That is just, and remember it's A2 here, that's 1/2. AC is AE plus EC. And then, of course, we have DE plus BE. And then we have our sine of alpha. All right, excellent. I think this is kind of as far as we can go, except there's one more thing we haven't really taken advantage of yet. And that's that AF equals CE and BG equals DE. And so if we make those substitutions, we're going to turn CE into AF, and then we're going to turn DE to BG. Then we get 1/2 AE plus AF. And then we're going to have BG plus BE. Then we have our sine of alpha. And whoa, hey, would you look at that? That's the same thing we have up here. Other than I may have changed the order of some things. FA is AF and comes after the sum there, but same exact total. And so what that means is that A equals A2. Now what was A2? A2 was the area of ABCD, which we know is 1, which means that A, the area of the triangle we're looking for, is also 1. Seems fantastic. Looks like we found a solution here, right? There's one big problem here. We kind of cheated a little bit in assuming that alpha was below pi halves. It was less than a right angle. And that is what allowed this altitude right here to land where it is on the figure, and for everything to sort of work out with the whole sine business that we pulled. If alpha is bigger than a right angle, that doesn't happen. And if it is exactly a right angle, then it also doesn't happen. And so we need to take all the cases. So we're going to write down, hey, if alpha is less than pi halves, A equals A2 equals 1, and then we have a solution here. Let's examine the other cases real quick. All right, so first we're going to take probably the easier case to handle, which is what if alpha is exactly pi halves, it's exactly a right angle. Well, that means that this is a right angle too, because, you know, this whole thing has to be pi. Pi minus pi halves is pi halves. And that would also mean that this is a right angle, and that would also mean that this is a right angle. What this also means is that we already have the height. It's literally just the segment. Oh, I forgot to write E here. It's literally just segment EG. The length of that would be the height corresponding to the base EF on this triangle. All right, so then we would have the area of the triangle A equals EF times a half, of course, times EG. And just as we did before, we'll expand this out. So that would be AF plus AE, and EG would be EB plus BG. All right, sick. Now we take the two triangles in the quadrilateral ABC and ADC as we did before, and we want to do the same thing, but you know, the right angles being super convenient give us a very simple expression here. So corresponding to base AC in triangle ABC, we have A2 equaling 1/2 BE AC plus 1/2, and then of course same thing for this triangle, we have 1/2 DE AC. Now let's use the distributive property to clean this up a little bit. So this would be 1/2 AC BE plus DE. And AC can be expanded out into AE plus EC BE plus DE. All right, so if you make the same substitutions that we did before, I think we can clearly see that these two end up being the same expression. So we know that if alpha equals pi halves, then A equals A2 equals 1 is also true. And so that just leaves the case where it's bigger than pi halves. And so let's cover that now. All right, so we're going to do this a little bit fast. So if you need to ever pause and think about like why something I say is true, please do so. I want you to fully understand everything here. I'm not trying to confuse you. If we have alpha right here being greater than pi halves, well, let's take this angle next to it. This would be beta, right? If alpha is too wide, then the altitude that we need to draw to find the height relative to base EF is actually going to be like something like this, all right? So this will be a right angle. And then we'll have angle beta sort of taking the place that angle alpha had in the opposite case. So we have the height, which will be length EG times the sine of beta. And of course, the sine of angle beta here will be the length of this altitude divided by the length of this big segment here, which would be the hypotenuse in this right triangle. And I know it might be kind of weird to think about because of the way I drew the figure, but this comes out to the result of the area of the triangle being 1/2. We're still using EF as our base, and then our height is going to be GE times the sine of beta. Okay. Now let's do some expanding outward. This is 1/2. EF is AF plus AE. And then EG is BG plus BE. And then we have all this multiplied by the sine of beta. Cool. How do we deal with the quadrilateral? Well, for similar reasons as we had that the opposite angle to alpha was just equal to alpha, this is just beta, you know? And since this we know is alpha, right? Well, then when we draw the height of this triangle relative to base AC, it will end up being that the altitude goes on sort of the beta side. And so it shouldn't really be a surprise, but A2 is going to be 1/2 AC. And then we have DE times the sine of beta. And then we have the other half of the quadrilateral, the other triangle, 1/2 AC times BE times the sine of beta. Now right here, we're going to sort of distributive property and expand the line segments at the same time. So this will be 1/2 AC turns into AE BE plus EC. And then we have DE plus BE sine of beta. And, let's make our substitutions. Oh, they're the same thing. Yeah. Alpha greater than pi halves. Leveraging the other angle, we get the same result. So I think I've proven that in any case, the area of EFG equals 1, and this is our final answer. And so this is a full solution. By considering all the different cases, we can prove what the area of this triangle is compared to the area of this quadrilateral using not very much at all. We have two known facts about geometry, and one of them is a definition more than it is a fact that you have to know. So that's kind of impressive. The reason I chose to present this problem in particular is because it illustrates something that I think is very important about not only math, but about any kind of learning you do throughout life in general. It's something that philosophically I hold close to my heart. This solution that you just saw is not actually that illustration. That's right, folks. Here's the big reveal. This is actually part 1 of a 2-part series of videos that I'm doing on this problem. Part 2, which I'm releasing tomorrow, yes, the next day after this has been uploaded, it will go into more detail and approach the problem from a different direction, and then it'll tie all these sort of loose ends together in a way that I hope is kind of satisfying. So stay tuned for that part, and if you're watching this from 24 hours or more after it was uploaded, second part's already up, so move on to it. Thank you all for watching, and I'll see you next time.